I am back. Your guy's back. How was lunch? Beef, chicken, everything? Yeah, it's pretty good. I actually love New Mexican food. It's so good, little salsas. Well, today I have a really great afternoon. I'm going to be with you for the next 2 sessions. And I'm talking about 2 topics that are really exciting for me, near and dear to my heart. First, I'm going to talk about Agentic AI, which I think everybody knows by now is completely revolutionizing compute, and especially revolutionizing PCs. I'm excited to talk about that. And I'm going to try to explain to you my simplified view of what's really happening. Because I feel like a lot of the times we talk about agentic AI or maybe even generative AI, and we skip over what's happening, and so you can't really appreciate the technology that we're building to make it better. So we're going to spend a little time on what is it and how does it work, and then I'll tell you effectively what is Intel doing to accelerate agentic AI on client PC. So it should be fun. I wish we could take questions because this is much more fun if we do questions. So if you want to just shout out a question, feel free. But in general, we'll see how it goes. Ready? Next slide. So to begin with, you guys have just experienced this dramatic rise of AI, and it's not just been PC, it's been everywhere. We started off with perception, with basically convolutional neural networks that were doing things like object detection, face recognition, stuff like that. Then we went on enhancing, where effectively models started removing backgrounds and improving faces and making everybody beautiful. COVID, I had such a good look in COVID, and that was all because of enhancement. Now we're into generative AI, and so things like images are being generated, movies are being generated, text is being generated, and that all happened because of a massive innovation in neural models called transformers. And transformers were invented many years ago by Google, and they have changed the world without a doubt. They have been adopted into a model format called a large language model, which we talked about last time. And those LLMs are taking the world by storm. LLMs are able to process and get trained on lots of data, lots of natural language, or lots of images, or lots of videos, and then somehow, it is so shockingly odd that these things work, but you put in a text, and they can actually reason. And it's very, very clear that there's something going on that's approaching more of the style of cognition that we have. So with all that, you can kind of see what we've looked at in the past. There's been coding is now done generatively, architecture is done generatively, language is done generatively, games are done generatively. So generation has changed everything. As a matter of fact, we have an application called Playground, AI Playground, which is open source downloadable, and it will allow you to easily experience some of these generative AI. That's actually a generated movie. So it's pretty cool. But things have changed. And it started changing a couple years ago, really accelerated this year, and we're now into the model of action. Action through agents, okay? So agents are different in the sense that they don't sort of react passively. They don't present you information. They act to make things change and do actions. So the way I think about it is agentic AI is really composed of 3 things. First, you have a model, which it turns out is just a large language model today. I guess it doesn't have to be a large language model, but all agents are. And what they do is they reason and reflect. So reasoning, we kind of understand. You kind of give it information, you give it a prompt, and it reasons through some kind of set of actions. But reflection is new, and reflection is when you kind of do something and you take the results from an external tool and you sort of pass them back through the language model, and it generates the next step. So reflection is sort of taking input from the world in real time and kind of updating your next step planning. These agents also interact with the environment. They know about applications, they know about tools, and they can actually make informed decisions on what to do next. And lastly, they also use quite a bit of memory. So they use memory for 2 things. One is short-term memory, and the other one is long-term memory. So if you hear all these words that I'm saying, if you really just step back, they are becoming very, very, very much like us. Okay, so if that's the case, what's the current trend? This is showing you something called context size. So context size is the amount of words in the case of a language model, the amount of words that you can give as a prompt. And what's happening with context sizes, it used to be like whatever you wanted to get a text, what's the color, what is lavender? And then you'd put that as the prompt. That was the initial context. Now contexts are much larger. Started off around 4K, which is about the size of an instruction manual. Now we're up to 128K or even larger on some of these models, which means that we're able to now give it instructions that are as large as a big book. So if you imagine, you're not just asking these models a question, you're giving them context that is an additional, I looked at how big is the Encyclopedia Britannica. It's millions of words, so it's not that big, but it is bigger than most novels. And it's crazy. And the same thing that's happening is the capability of these models, what they can do is getting much, much more impressive. We've moved up from sort of like my level of intelligence, about 20% of average. Then we've gone past most of my friends, which are about 50% of intelligence, and they're actually up to about 76% of a human expert. And this is just a model that is, no more than about 8 billion parameters. So the trends are very clear, but the question is, what is really happening here? So I actually decided to start off with a demo. And what this demo is going to be is of an application called SuperBuilder, which is open source. We make it available online. You can download it. I have Craig here to help me. So Craig, thank you for coming up.
Oh, my pleasure.
Why don't we start with describing what are we looking at on your screen and what exactly is SuperBuilder?
Yeah, let's go ahead and take a look. So here I have running on brand new Panther Lake hardware on this little beautiful dev kit that we have. And what we're going to be running in this application that you're seeing here is AI Assistant Builder. This is an open source piece of first-party software from Intel. You guys can download it today for free. I highly suggest it. It's awesome.
It's pretty cool.
But now in its newest version, this LLM management kind of chatbot interface also integrates all those new agentic tools that we were just talking about here.
Yep.
So let's go ahead and take a look at, and we're just going to go ahead and kick off a request.
Okay.
And we'll start running through how the LLM is handling these cases and how it's dealing with its agents.
Great.
So what we've asked it to do is we want to make an Intel presentation, do some market research, and put together a PPT on, well, our AI PC capabilities. So here it's gone ahead and kicked off, and it's actually calling a particular agent, which is our slide maker that we have going on here. And actually, if you see up in the upper right-hand corner, I'm going to go ahead and open up our MCP manager. And this is the new protocol, model content protocol, that really kind of is the next generation of the API, where we're able to see both AI agents are able to go ahead and communicate with an online service super easily and without the super stringent capabilities of the input-output of an API. It's just two agents talking together. Some cool LLM conversation.
Okay.
And as a result, it's gone ahead and called its tools. It advertises as an MCP, hey, I can do that PowerPoint for you.
Okay.
And so the main model then says, well, let's go ahead and do it. And well, it's just popped up right here for us already. So
okay, that's
it's
cool.
Pretty dang fast.
Yeah.
So it's actually still going in right now. Oh, you guys are too nice. Oh, thank you. Love applause for a demo. These are harder than you think.
It's very cool.
But as you can see, it just popped up. We're looking really great there. And so really going back to having those tools available, these are the things that are going outside using authentication in your stead to make some cool stuff like that happen. But I'm guessing you're going to do a little deep dive.
I'm going to do a deep dive, but thank you very much, Craig.
Thank you.
Appreciate it. Okay, that's cool, right? So before I begin the deep dive on what's happening here, I want you to know that this demo is available in the Experience Zone, and you can dig into it to your heart's degree. There is so much to know and so much to understand here, so I'm pretty excited about it. This is actually what really happened there. So if you look on the right-hand side here, or on your left, it goes from the front or the left to the right here, and it starts with user input. Then there's something I call an orchestrator agent, an agent LLM, agent memory, and an MCP server. So what's really happening here is there are two agents running locally. Both of them are Qwen 3 models, so they're large language models. They're implemented and optimized using OpenVINO, which I'll talk about in a little bit, and they're running live on Panther Lake. And the first agent's job is to figure out what problem are we trying to solve. And what really has changed is now with these very long prompts, you can tell an LLM effectively what your job is. And when you tell an LLM what your job is, you say, this is what your job is, this is the tools that you have available, please do something. And so the agent, the LLM, when you start inferencing it, generates text that represents the actions that it wants to take. This is assuming it's all text. It doesn't have to be text, of course. This could be some kind of binary encoded machine-only knowledge, but in general, it's easier to think about the whole thing as if it was text. All right, so let's walk through what's happening. Step number 1 in my walkthrough is right here. Okay, so on the right-hand side, this black box, I guess it's, yeah, you're right. That black box is the text that the tool is generating, and the block in the middle is the user interface that we make available. So the first thing that we do is we get a prompt from the user. He just types it into the text box. We remember the prompt. Pretty simple. Next thing that happens is we have to create the context. Remember, the context is the words that we're going to feed into the first LLM. And in this context, it's made up really of 2 or 3 main things. The first thing is we have some pre-baked text that says what your job is. In this case, we're going to say something like, you're an agent, and please be honorable and do good things. And you know, based on what the user says, please try to accomplish that task. And we then tell it what resources are available to this orchestrator. The resources they have in this case, you have access to another agent. And that second agent is called SlideMaker. And you can see in the text, it's just a prompt. All we're doing is giving an LLM a prompt. Then we're going to tell the LLM what tools are available. So you have access to an external resource called ChatPPT, and you have access to a local resource that will open up a PowerPoint. So it's actually not magic. What we're doing is creating a large context that gets fed into an LLM, and the LLM just generates words. But in this case, the words are not random. The words are agentic action. So everybody with me so far? Any questions? We're all good? It's just an LLM. It's just doing context. Here we go. Next step is the orchestrator initiates the prompt, sets up the context of the next agent. So now what you're seeing for the first time is an agent communicating to another agent. But when you really think about that, that's just more text. So in this case, for the second agent, we have a system input prompt, which is coming from SuperBuilder. And that says, you're a helpful assistant. Please accomplish the user's task and execute a series of commands until you complete the user's request. And then we tell it from super agent, from the orchestrator, please call this tool. Right? So please call ChatPPT, and here are the commands that you should send to ChatPPT. So it's, again, just an inference. It's just an LLM. And so the second agent starts cranking its letters and cranking its numbers, and it's using its transformers, running locally on Qwen 3. And it then generates an output. And the output says, please call ChatPPT. So that text is parsed by a local service that's running on our PC. And it says, oh, I saw this LLM said call ChatGPT, so it converts it to an MCP call. As Craig mentioned, MCP is a protocol for doing remote access to effectively services for agents. And that kicks off the thing in the cloud. And the thing in the cloud is another agent called ChatPPT. That's running somewhere else. But eventually, that agent responds back, and it says, good news. I did your PowerPoint for you. And it's ready, and here's a link. And then, just like before, only this time it's the agent LLM, the SlideMaker, it's going to do reflection, which means it's going to take the response from the remote MCP call, it's going to put it back into its context, and it's going to generate words. Only this time the words are, hey, I see that the PowerPoint is generated. Why don't we go ahead and open up the UI and tell the user we're done? So when you do all that, you call a local service to pop up the PowerPoint, return a prompt back to the user, and we are done. That's your first walkthrough of Agentic AI. It's just LLMs that are prompting each other and LLMs that are creating calls to services using standardized interfaces. Okay, so I mentioned already this morning that Panther Lake is designed for this work. We have up to 180 tops of performance for AI. It's divided by the CPU at 10, the MPU at 50, and the GPU at 120. But what's really kind of important about this is how do we take these large language models, which are billions and billions of parameters, and get them to run on a PC? And the process of doing that is called quantization. Okay, so the agentic workflow is pretty simple. We start here with somebody creates a model, it's using one of these frameworks. You can actually create a model yourself. You can fine-tune a model, but they're all using some framework. Then that goes into our quantization tool, which is the NNCF. NNCF has every algorithm we can think of, and it's basically how do I shrink a model down without losing accuracy. It's been upstreamed into Microsoft Olive. So if you think about it, this whole process of quantization is about, hey, how do we get our tools into the cloud? How do we make normal frameworks use our tools to do quantization? So that has all been done. The next step after quantization is performance evaluation. We have our vTune application that is perfect for that task. It constantly gets updated to become more agentic workflow analysis friendly. And lastly, we got to figure out how to run these things. So we have a complete software stack called OpenVINO. I'm going to explain a little bit about OpenVINO because I think people get confused about what it really is, but I'll make that clear. Of course, we also support the Onyx runtime and others. And finally, it lands on a CPU, GPU, or NPU. And that's all pretty much automatic these days. So it's a pretty expensive and hard to do workflow, but we've been investing in it for many years. All right, so let's talk a little bit about quantization. That is the critical step that allows us to target a specific model on our hardware. And so we've done it 3 different ways, depending on the use case of an application developer. The first one is we have pre-baked models. We have a team that applies our quantization technologies, and over the last couple of years, they have pre-converted and pre-quantized more than 300 models. They're available on Hugging Face, which is an open source repository, and you just look for Intel optimized models, and you'll get a whole list. So this is probably the most common and easiest way if you're an application developer to get an optimized model. The second path I call DIY models. And a DIY model would be, I have a model, I maybe fine-tuned it, or I'm doing some kind of update to it, and I want to re-quantize it. Well, you can use our NNCF. Again, it's a full set of suites. It does a whole bunch of algorithms, and those algorithms are world-class right now. The last thing we do is we have dynamic quantization. So built into our runtime, which I'll talk about in a little bit, it's constantly evaluating the data widths and the data precision, looking for optimization opportunities. So even if you give a gigantic model to our runtime, it will, of course, as you enable it, it will selectively prune that data down to run faster. Okay, so with optimization out of the way, it's time to talk about the stack. And the software stack here, again, is a massive undertaking. The way to think about this is for any AI inference application, there's some kind of user interaction layer, there's some kind of prompt, and then there is a big blob that is your AI agent. In this case, there's application logic, but then there's a layer that's the model layer, right? Could be multiple models, it could be one model. And you're either going to have your model in format of Onyx or PyTorch or that other thing or whatever. There's lots of model formats. And at the end of the day, they're all going to run and be optimized, quantized. So you're going to get that list of models that are available to the application. And finally, they execute on your LLM inference stack. And that will then generate responses and reports, and the whole thing will cycle. So that's my view of an agentic software stack. You can see on the right here, over here, I have a little gray box, and it says OpenAI, API, MCP, and A2A. Those are the typical external interfaces that these type of applications use. MCP is the most common. Okay, and that's how they call into remote databases or into tools or other agents. So with this software stack, you can see the big part is this thing that's called Intel AI Inference Software Stack. So I want to dive into that. Now, the AI inference software stack has a bunch of pieces. On the left-hand side here, we call it our most performant path, and it uses a native OpenVINO API integration. So you can have an Onyx model, a PyTorch model, but they all go into the OpenVINO graph. Effectively, it's a DLL that gets loaded into your application, and it does graph optimization. Eventually, it goes through a bunch of other optimizations, but it lands, and this is the key part, it lands in the OpenVINO runtime. Now, the OpenVINO runtime is effectively our inference layer. So it kind of deals with all the complexity of our optimized kernels, like how do I do a convolution on Intel? Should I do on the CPU or the GPU or the MPU? All of that is abstracted in the OpenVINO runtime. And it's horizontal, meaning the OpenVINO runtime runs all the time. If you're doing inference on Intel, you don't only run the OpenVINO runtime when you have a OpenVINO API application. You also run the OpenVINO runtime whenever you have a vendor-agnostic application. And one of the interesting things on this vendor-agnostic path is not just PyTorch and ggguff, but also Onyx. That's the window path. So if you're doing a Microsoft Windows-based AI application, they just announced, in partnership with Intel, something called Windows ML. Windows ML is hugely important, and what it does is it standardizes the way that AI applications are going to be written in the future. And it's really important because it's vendor neutral. So you won't see, like CUDA, if CUDA, none of that. This is all vendor neutral. It allows the ecosystem to grow quickly. So we love Windows ML. Windows ML works through multiple layers, but again, lands on the OpenVINO runtime, which is very exciting. We can leverage all of our effort into improving inference across all platforms. Now, this Microsoft path is super important. We actually been working with Logan and his team for a long time. He has a very nice quote for us. Microsoft's collaborating closely with Intel to enable locally accelerated AI agents on Copilot+ PCs. And again, that is one of the critical things about working with Microsoft long term. We can partner on technologies that will change the platform dramatically. And again, this stack means that you can run one application and you write it, you might use an Onyx model, it'll go all the way through the WinML stack, land on the OpenVINO runtime, and get accelerated on our hardware. Okay. So, this runtime, I hope you're understanding that the runtime is very important for us because that's where a lot of our optimizations exist. And so this is showing you the problem that we're facing. There's lots of different types of agentic models. There are things that are very simple, basic functions, long-term reasoning models, all the way up to autonomous actioning models. So the size of these models changes dramatically. The bandwidth that they need changes dramatically. And we need new technologies up and down our software hardware stack to make it work well. So we do. This is not meant to be read. It's just it's a roadmap, if you think about it. Starting from the bottom, there's different types of agentic AI models. And if you look at the column that's called software enabling, these are all new techniques that we're implementing in our OpenVINO runtime or other layers of our software stack. The specific ones I want to call out are effectively the lightweight graph RAG, the batch inference and indexing, and the KV cache. The reason those are important is because they have a significant importance on performance today. So there's been great work by the team, and I'm super excited about the progress. This is stuff that is all committed to be ready around the time of Panther Lake launch, enabling all of these different style of agentic AI. So what I'm excited about is to show you a demo. We're going to show you those three technologies, the dynamic quantization, the KV cache, and the page detention. And the way I'm going to demo it is a kind of before and after. We've already implemented these things in the OpenVINO runtime. So the way to demo it is kind of say before and after OpenVINO. So I've got Craig back up here. What I want to do is roll through a live demo of this stack. On the one side, we're going to have OpenVINO 2024, which would be the before the fixes. And on the other side, we're going to have OpenVINO 2025.3. Both of these examples we're going to show are inference with a Llama 3.1 8 billion parameter model, and we're using a large context of 32K. That's a Damian note, by the way. So, Craig, what do we got?
Oh, we're going to go ahead and kick it off. So, Mr. Tap, let's go ahead and run both of these that we're going to have on both of our screens here. And on your left-hand side that you're going to see the pacing of what we have in 2024.
I see.
And over on your right, and these are both Panther Lake systems, by the way, on the right-hand side, you're looking at 2025 OpenVINO.
Okay.
So, just a good snapshot as we go back to the Wayback Machine and see how far we've come with building this new framework, especially the new capabilities of it. And we know that OpenVINO is the way to get the most out of your accelerators.
Yeah.
And in that time jump that we've had, not only do we get better performance, but we're also looking at a reduction in memory usage just in software efficiency.
Absolutely, really
that we're showing here.
So all right, so the way to think about this demo is on the left, it's the rate of text generation, and on the right, the rate of text generation. These are both running, what was the model? Llama 3, right?
Llama 3,
yeah,
correct.
8 billion. And you can see we're about twice as fast.
Yeah, about there. You know, we'll have some actual hardware numbers for you guys to be sharing pretty soon, but you know, to these eyes right here, looks like this one's fast.
All right, thanks, Craig. Appreciate it. All right, let's come back to the slides. And I really think it's pretty cool that this OpenVINO world is moving forward so quickly. It's got a strong roadmap, and I'm excited to be investing there. This is kind of summarizing the current performance of old versus new. So gray is 2024, blue is 2025. In this first chart, we're showing you context size. So as the context size increases, 2024, and it's actually showing you time to first token. So you want the bars to be lower, and you can see 2025 is much faster to first token than 2024. As a matter of fact, when you get to 64K context, 2024 could not even handle it. That's where we did a lot of that KV caching and the chunking of the model. By chunking the execution, we can actually support much larger context. The second graph is showing you, again, context size and peak memory consumption. So another key limiter of performance on these platforms is the bandwidth that the model requires. So, you know, having those caches and now having technologies to reduce the memory footprint is critical. You can see, again, the memory footprint kind of exploded with 2024 OpenVINO and 2025 OpenVINO. Collection of technologies brings that way down. Lastly, as context size grows, token rates decline. But again, you can see our 2025 OpenVINO doing much, much better than 2024. If you summarize this, do some division. We are twice as fast to first token. We are 6 times better on memory consumption and twice as fast on tokens per second. So the progress on the OpenVINO stack is pretty spectacular. And I think we're going to try to do a better job of separating the OpenVINO runtime from the OpenVINO integration stack so people can start appreciating it. Okay. So that's Panther Lake. It is built for agentic AI. We have 3 different engines delivering a total of 180 TOPS. We have a massive investment in software all the way up our stack with the OpenVINO runtime, but we also have all the layers above and below that. It's really quite phenomenal. We have a close partnership with Microsoft for Windows ML, which is really spectacular. And I just expect this to keep getting better at the same rate for some period of time. And we also obviously work across the ecosystem. You can see Microsoft, PyTorch, Onyx, TensorFlow. We have a huge Hugging Face repository, of course, OpenVINO and Onyx. So it's a pretty nice package, and it will continue to deliver for PCs as we get closer and closer into the agentic world. And with that, thank you very much. Hopefully we'll talk at the break, and then I'll be back in a little bit for gaming. Gaming is going to be great. All right, thanks a lot.